Fourth and last case. What is left to consider? Well, it's left to consider the case in which lambda 1 and lambda 2 are complex. So they're not real anymore. If they are complex, then it has to be that lambda 1 is the complex conjugate of lambda 2. And it has to be that psi 1 is the complex conjugate of psi 2 up to a constant. Remember that eigenvectors are always defined up to a constant. Complex eigenvectors are defined up to a complex constant. That means that in case of R2, we have a lot of freedom of choosing things. But let's assume that psi1 is just the complex conjugate of psi2. So this constant in the middle is just 1. So we only have to take care of lambda 1 and psi1. In this situation, we're back to the usual formula. So Cx, the general solution, is equal to C1 psi1 exponential of lambda 1t plus C2 psi2 exponential of lambda 2t. Because we know that lambda 1 and lambda 2 are strongly related, then we can rewrite this as C1 psi1 exponential of lambda 1t plus C1 conjugate psi1 conjugate exponential of lambda 1 conjugate times t. And we want to unwind this in order for it to be easier, because in this case C1 is complex itself and we are expecting a real solution. So we can do some changes. We write lambda 1 as alpha plus I beta, psi1 as v plus iw, and C1 as a plus ib. We write everything down. And we use the Euler formula to write the complex exponentials as a sum of sines and cosines. And we retrieve this very pretty formula. I'm going quite fast. You should have done these same steps to build your code in lab 4. I heard from the grader that there have been some hiccups on the formulas themselves. So I'm writing them down for this reason, but you should be familiar with these steps, even though mistakes happen easily with so many terms. So now we have two terms that look very similar. There are just some different signs in the middle of the parentheses. And we can write, here I multiplied the first two parentheses out, and then I will sum with respect to cos beta and sin beta. So if going through every step, I get to the point in which I have exponential of alpha t, the real part of my eigenvalue, times cos beta t, beta is the imaginary part of the eigenvalue, times c1v plus c2w, close parentheses, sorry about that, plus sine of beta t times minus c1w plus c2v. V and w are the real component of my eigenvector, and w the imaginary component of my eigenvector. Notice how I have to be consistent in keeping the signs of v and w's. So I choose one setting and I keep it. Because c1v plus c2w is multiplied by cos beta and exponential of alpha t, that both go to 1 when t is equal to 0, then we have that c1v plus c2w is equal to x0, our initial condition, if we set initial conditions at time t0. Then I will introduce this y0, that is minus c1w plus c2v. C1 and C2 are determined once we determine x0, so it should not be a problem to determine y0 once we have determined x0. So if we take the R2 plot, we can plot x0, we can find y0, and what we know is that we're going from x0 to y0, because going back, when beta t is going to be such that the cosine is going to be 0 and the sine is going to be 1. So we're moving from x0 when t is equal to 0 to y0 when beta t is equal to pi half. So we're moving from x0 to y0. If alpha is equal to 0, so there is no multiplication by the exponential, we're actually reaching exactly y0. And then we have this situation in which we're orbiting from x0 to y0 to minus x0 to minus y0 and back. We call this situation a center. We have lambda 1 and lambda 2 exactly imaginary. We can also take our code and see what happens when we put imaginary eigenvalues. Remember, in case of imaginary eigenvalues, they need to be complex conjugate. So one needs to be, has a different sign for the imaginary part, and the same must hold for the two eigenvectors. They need to be complex conjugate. So for example, we could have something like this. And just to make MATLAB, to be clear with MATLAB about what I is, writing one I explains that it is an imaginary number. So we have complex conjugate eigenvalues, purely imaginary, and complex conjugate eigenvectors. And we retrieve what we expect to be a center. So everything is orbiting around 0, 0. If alpha is negative, while we're moving from x0 to y0, we are undershooting a bit. We are being dragged towards 0. So we are not making it to y0, we're a bit short off, and we spiral towards 0 instead. Notice that if y0 is much further away from 0, we might go first away from 0 before going towards 0. Again, we can use the MATLAB code to check these options. We have imaginary size, and now we have a negative real part. And you see, maybe it's a bit rough, but you see something spiraling towards the center. If A is positive, if A is positive, on the other hand, the exponential is pushing us away from 0. So if we go from x0 to y0, we are overshooting. We're getting further away from 0, and we're spiraling away. And backward in time, we have the same shape as we had in the previous situation. So we're backward in time, we go towards 0, and we call this the unstable spiral. Everything spirals away from 0. And the ratio between the real part and the imaginary part is the one that decides how fast we're moving away with respect to how much we're swirling around.